So, now let us see how f2t minus f1t would look. It is very easy to see that f2t minus f1t has an appearance like this. Let me flash them before you, f2t and f1t, just for a second here, so that you get a feel. This is f2 and this is f1, and visualize subtracting this from this. What would you get? A function that looks something like this. So, I have the time axis here. So, if I mark the intervals of size t there, something like this. Maybe this has height h1 and this has height h2. Let me mark h1 and h2 on this diagram too. So, this is h1 and this is h2. Of course, so is this. Simple enough. Now, if we look carefully, we can construct all of this by using just one function. And what is that function? Suppose I were to visualize a function like this. One over the interval from 0 to 1/2 and minus 1 over the next half interval. This is the point half, this is the point 1, point 0, 1 here and minus 1. And let us give this function a name, let us call it psi of t. In fact, this is indeed what is called the Haar wavelet. Haar, again the name of the mathematician. It is very easy to see that using this function, I can construct any such f2t minus f1t. Indeed, if I were to take this function, stretch it or compress, whatever might be the case, depending on the value of capital T, dilate is the more general word. So, if I were to dilate this function to occupy an interval of t and bring it to this particular interval of t. So, I dilate that function psi t and bring it to this interval of t, and then I multiply psi t so dilated by the constant h1. Of course, h1 should be is an algebraic constant, it should be given a sign. Here, for example, h1 should be given a negative value, because we have started psi t with a positive minus 1 here. Similarly, h2 has a positive value here. So, in other words, this segment of f2t minus f1t is of the following form. Some h1 times psi of t dilated by t plus h2 times psi of t minus t dilated by t. So, here this is both dilated and translated, all right. In other words, in general, when we start from the function psi of t we are constructing functions of the form psi t minus tau by s, where of course s is a positive real number and tau is real. This is the general function that we are using as a building block, different values of tau and different values of s. Of course, here at a particular resolution, at a particular level of detail, the value of s is only 1. For example, when we are representing the function on intervals of size t, we take s equal to t. If we were to represent the function on intervals of size t by 2, then s would become t by 2 and so on. Then what we are doing in effect is dilating and translating. So, now we introduce those terms. Tau is called a translation index or translation variable, and s is called a dilation index or dilation variable. And we are dilating and translating, or we are constructing dilates and translates of a basic function. Dilates and translates of psi t capture the additional information. In f 2 t minus f 1. Let us spend a minute in reflecting about why this is so important. What have we done so far? Just looks like very simple functional analysis or just a very simple transformation or algebra of functions. What is so striking in what we have just said? What is striking is that what we have done to go from t to t by 2 can also be done to go from t by 2 to t by 4. Not only that, what we have done to go from t to t by 2, in other words, for intervals of length t to intervals of length t by 2 all over the time axis, can be done all over the time axis to go from intervals of size t by 2 to intervals of size t by 4. And then you could go from intervals of size t by 4 to intervals of size t by 8, t by 16, t by 32, t by 64 and what have you, to as small an interval as you desire. Each time what you add in terms of information is going to get captured by these dilates and translates of the single function psi t. A very serious statement if we think about it deeply enough, that one single function psi t allows you to bring in resolution step by step to any level of detail. In fact, in formal language in functional analysis, we would put it something like this. You know, in mathematics, in these arguments of limits and continuity and so on, or in some of these proofs related to convergence, there is this notion of the adversary and the defendant. So, here the defendant is trying to show, the one who makes the proposition is trying to show that by this process you can go arbitrarily close to a continuous function, as close as you desire. Now, as close in what sense? Well, it could be in terms of what is called the mean squared error or the squared error. So, let us formulate that adversary proponent kind of argument here. So, what we are saying is the proponent says we can go arbitrarily close to x t, to a continuous function x t by this mechanism. Arbitrarily close in what sense? In the sense, if x a is the approximation at a particular resolution, and if x t is the original function, then if we take what is called the squared error, so we look at x e t, that is x t minus x a t, and integrate x e t the whole squared, the modulus whole squared actually, over all t. We will call this the squared error, script e. Then the adversary or opponent says bring e to the small value let us say E 0, and the proponent says certainly here is the m such that t by 2 raised to the power of m is okay. So, that is the idea of proponent and opponent here. The adversary or the opponent gives you a target. He says, I want the squared error to be less than this number E 0, and the proponent says, well, here you are. If you make that interval of size t by 2 raised to the power of m, lo and behold your error is going to be less than or equal to E 0. And what is striking in this whole discussion is, no matter how small we make that E 0, the proponent is always able to come out with an m, such that t by 2 raised to the power of m, I mean piecewise constant approximation on intervals of size t raised to the power of t by 2 raised to the power of m would give you an approximation close enough for that small E 0. We need to spend a minute or two to reflect on this. It is a serious thing we are saying. In fact, let us for a moment think on how this is dual to the idea of a representation of a function in terms of its Fourier series, for example. In the Fourier series representation, what do? We say, give me a periodic function, or for that matter, give me a function on a certain interval of time, let us say an interval of t, size t. If I simply periodically extend that function, that means I take this basic function on the interval of t, I repeat it on every such interval of t translated from the original interval. So, suppose that original interval is 0 to t, then repeat whatever is between 0 and t, between t and 2 t, between minus t and 0, between minus 2 t and minus t, between 2 t and 3 t, and go on doing this. So, you have a periodic function. Decompose that periodic function into its Fourier series representation. So, what am I doing? In effect, I have a sum of sinusoids, sine waves, all of whose frequencies are multiples of the fundamental frequency. What is that fundamental frequency? In angular frequency terms, it is 2 pi by t. In Hertz terms, it is 1 by t. So, in Hertz terms, you have sine waves with frequencies which are all multiples of 1 by t, and an appropriate set of amplitudes and phases assigned to these different sinusoidal components with frequencies of multiples of 1 by t, when added together, would go arbitrarily close to the original function. Of course, the original periodic function on the entire real axis, or for that matter specifically on the interval from 0 to t, if you restrict yourself to the function from where you started. So, not only does the Fourier series allow you to represent by using the tool of continuous functions, analytic functions. Remember, we talked about sine waves in the previous lecture. Sine waves are the most continuous in some sense, the smoothest functions that you can think of. The derivative of a sine wave is a sine wave. The integral of a sine wave is a sine wave. When you add two sine waves of the same frequency, they give you back a sine wave of the same frequency. So, sine waves are the smoothest functions that you could deal with, and even if you had a somewhat discontinuous function on the interval from 0 to t, and if you use this mechanism of Fourier series decomposition, you would land up expressing a discontinuous function in terms of extremely smooth analytic functions. What would you be doing in this Haar approach that we discussed a few minutes ago? Exactly the dual. Even if you had this continuous audio pattern, you would decompose it into highly discontinuous functions which are piecewise constant, constant on intervals of size t at the resolution t, on intervals of size t by 2 at the resolution t by 2, and so on and so forth. Now, just as in the Fourier series representation, you have this proponent opponent kind of argument, that is, for a reasonably good class of functions, even if they are discontinuous, even if they have a lot of non-analytic points and so on, for a reasonably wide class of functions. Remember, in the Fourier series, that wide class of functions is captured by what are called the Dirichlet conditions. Now, I will not go into those details here, but there are certain kinds of conditions, very mild conditions, which a function needs to obey before it can be decomposed into the Fourier series, or in other words, before the Fourier series can do this job of representing that discontinuous function in terms of highly continuous and analytic smooth functions. So, similar set of conditions does exist even for the Haar case. I mean, if one really wishes to be finicky, one does need to restrict oneself to a certain subclass of functions, but again that restriction is not really serious in most physical situations. For the time being, in this course, we may even just ignore that restriction.